Welcome to the Deep Dive. We take fascinating sources, pull them apart, and get to the core insights you need. Today we're tackling, well, one of the biggest questions there is. Why do we age? Why does everything seem to slow down, to fade? And why didn't evolution over all this time fix what feels like a pretty major bug in the system? It really does seem like evolution just, left aging on the table.
That's exactly it. And that thought is right at the heart of our deep dive today. We're drawing on ideas like evolution's oversight, hacking longevity. And the really striking part is this. Aging probably isn't some fundamental biological law that evolution perfected. It's much more likely a low-hanging fruit kind of problem. Why? Because evolution, for some very specific reasons we'll get into, just didn't really optimize for super long lives.
Low-hanging fruit. That sounds solvable.
Potentially, yes. It suggests modern science might find it surprisingly, well, tractable, maybe even relatively straightforward to extend our healthy years using, genetic and epigenetic tools. We wouldn't be fighting some perfectly tuned ancient mechanism. We'd be tweaking parts that evolution basically didn't fine-tune. It's kind of a biological hack.
Okay, that completely changes the perspective. So our mission today, figure out why. Why did evolution overlook longevity, understand the surprising logic behind it all, and then crucially, what does this mean for us now, for hacking our own biology? Get ready, because this might just change how you think about getting older. The Deep Dive, unpacking evolution's longevity puzzle. All right, let's really dig into this. Instinctively, you'd think living longer and healthier is always better, right? So why didn't evolution push for that? What was going on in, prehistoric times that stopped it?
Yeah, if you rewind through most of human history, the key factor is what biologists call hazard rates. Think about our ancestors' lives. Constant danger, predators, starvation, accidents, conflicts, and especially infectious diseases. These weren't rare events, they were everyday risks.
So just surviving day to day was the main challenge.
Absolutely. The simple truth is, very, very few people lived long enough for natural selection to really start favoring genes that promoted, say, excellent health at age 80 or 90. It's like designing a car engine to last 500,000 miles when most cars historically got wrecked long before that. Why invest the extra resources?
Okay, so even if a longevity gene popped up, giving someone great health later in life,
it just wouldn't have made much difference evolutionarily. Most people wouldn't reach the age where that gene's benefit kicked in. Something else, an infection, an accident, would likely get them first.
So that gene rarely got passed on simply because its owner didn't live long enough.
Exactly. It rarely got tested by selection, which leads to the next logical step. If evolution wasn't focused on extending life way past the reproductive years, what was it focused on? What was it optimizing?
And I'm betting it wasn't planning for a nice long retirement by the fire.
Definitely not. Evolution poured its efforts into youth optimization versus longevity, the traits that helped you survive and, critically, reproduce early in life. Those were the absolute priority. From the gene's perspective, the main goal is simple. Get copied into the next generation. Anything after that is, well, less important.
That sounds like the disposable soma idea, right? That the body is just a temporary carrier for the genes.
Precisely. Our body, our soma, just needs to last long enough to reproduce successfully, investing resources and maintaining it perfectly long after that point. From evolution's standpoint, that's potentially wasteful.
It's a stark view, but it makes sense in a world of constant threats. You need peak performance early on.
You do. And think about fluid intelligence. That's your ability to solve new problems, think on your feet, adapt quickly, raw processing power, basically. When does that peak? Usually around ages 25 to 30.
Right, when you'd be learning crucial survival skills, finding a partner, or maybe starting a family.
Exactly. That's not an accident. It's evolution prioritizing the cognitive tools most needed for survival and reproduction in that dangerous early adult phase. It's interesting because other kinds of intelligence, like crystallized intelligence, your stored knowledge, your experience, that often keeps growing. But evolution favored that sharp, youthful, problem-solving ability.
Okay, this is where my mind starts bending a bit. If life was so tough and resources scarce, could living too long actually have been bad from evolution's point of view? Could there be a cost?
That's a really sharp question, and yes, the sources definitely explore this trade-off problem. There are real energy and fitness costs to living a very long time. Think about all the biological upkeep, constantly repairing cells, fighting off entropy, maintaining complex systems for decades. It takes a huge amount of energy and resources.
Resources that could maybe go elsewhere.
Exactly. From that selfish gene perspective we talked about, imagine the choice. Maintain one 70-year-old who's past reproductive age and potentially needs support, or funnel those resources towards, say, two healthy 20-year-olds who are actively having kids. For propagating genes, the latter is often a better bet. Evolution, dealing with limited budgets, had to make these kinds of harsh calculations.
So it's less about designing us to age and die, and more about just not investing heavily in extreme long-term maintenance.
That's a great way to put it. And this leads to another fascinating idea. Could aging actually serve a kind of regulatory function? The source uses this analogy from machine learning aging as a length regularizer.
A length regularizer. What does that mean in this context?
Okay, so in machine learning, sometimes you add a penalty to stop a model from becoming overly complex or taking too long to run. It forces efficiency. You can view aging in a similar way. An extremely long lifespan is, in biological terms, a very long process. It requires constant maintenance, accumulates damage like mutations. So aging, by limiting that individual lifespan, acts like that regularizer. It ensures population turnover.
Clearing out older individuals makes way for new ones.
Potentially, yes. It keeps the population dynamic, allows new gene combinations to be tested, maybe makes the species as a whole more adaptable to changing environments. Again, it's not necessarily designing for death, but it's a consequence of not designing against it, because the costs of that indefinite maintenance outweighed the benefits for the gene pool.
Wow, that's a really different way to think about it, the individual lifespan serving the species' adaptability. But it does make you question that idea of evolution as this perfect engineer, always finding the absolute best solution. What stops it? Why didn't it overcome these trade-offs and just make us long-lived and reproductively successful?
Right, and that's key. Evolution isn't a perfect optimizer. It's powerful, but it works under some serious constraints. Think of it like a complex computer program. The sources compare genomes to parameters and natural selection to the optimizer, maybe like training a giant neural network. Now, theoretically, a big enough network can learn almost anything, but practically, it runs into problems, it gets stuck, the learning process is too slow, the data is messy. Evolution's the same.
What kind of practical problems does evolution face?
Well, several big ones. Take the mutation rate. It has to be balanced just right. Too high. You risk lots of cancers, unstable genes, non-viable offspring. Too low. You don't generate enough variation to adapt to new challenges like new diseases. Evolution finds a workable middle ground, but it's not necessarily the perfect rate for individual longevity.
Okay, a balancing act. What else?
Population size is huge. It limits how many different genetic ideas or mutations can be tried out at once. Small populations just can't explore the genetic landscape as effectively. And maybe the most important constraint, historically speaking, the main selective pressure. For the vast majority of human evolution, the biggest threat wasn't aging. It was infectious disease, predators, starvation. That's where evolution focused its problem-solving efforts. Extending lifespan to 100 just wasn't the top priority.
Because you had to survive childhood in your 20s first.
Precisely. You had to get past those immediate hurdles. Longevity was a luxury evolution couldn't afford to focus on.
I love how the source brings in these analogies from totally different fields, like computer science. How does machine learning, and maybe reinforcement learning, help us get a better handle on this whole aging puzzle?
They're surprisingly helpful, actually. We touch on the machine learning analogy with the length regularizer. Think of it like preventing overfitting in biology. An organism that invests everything in perfect, indefinite self-repair might be too specialized, too resource-intensive, maybe less adaptable. Aging prevents this kind of biological overfitting, keeping the system leaner, focused on reproduction. The genome is the code, selection is the training process, but it's working with noisy, real-world data over millions of years.
Okay, the regularizer makes sense. What about reinforcement learning? How does that fit?
The reinforcement learning RL analogy frames evolution as a massive long-horizon RL problem. In RL, an agent learns by getting rewards or punishments for its actions. For evolution, the reward is basically successful reproduction, getting your genes into the next generation and ensuring their survival. But think about the time scale. The feedback loop for that reward stretches over decades: childhood, puberty, mating, raising young.
Compared to an AI learning a game where it gets feedback instantly.
Exactly. Evolution gets this incredibly delayed, sparse, and noisy reward signal. Did that specific trait really help offspring survive 30 years later? It's hard to tell definitively. This massive delay makes it extremely difficult for evolution to fine-tune traits that only pay off very late in life, like extreme longevity. The signal just isn't clear or timely enough.
So wrapping this part up, evolution basically had bigger fish to fry, short-term survival, early reproduction. Those gave clear, immediate feedback. long life didn't.
That's a really good summary of it. The selective pressures just weren't there to push for extreme longevity.
Okay, so here's the pivot. If aging wasn't strongly optimized, if evolution kind of left it as an unsolved problem, what does that mean for us now? What are the really exciting takeaways for science today?
This is where it gets incredibly hopeful, I think. The core argument, like from Kimmel, is precisely because aging wasn't strongly optimized, we might actually be able to hack it. It's potentially much easier than trying to change a system that evolution perfected over millennia for a specific function. We're dealing with something that was more of an afterthought or a side effect.
So we're not fighting against a fortress of optimized biology, but maybe finding unlocked doors.
That's a fantastic analogy, yes. We can potentially identify and tweak the specific genetic or epigenetic pathways, the levers that control aging, precisely because evolution didn't build super robust defenses around them. Other things were just more important back then.
That feels like a massive shift in thinking. Can you give us some real-world examples, like how might this hacking actually work? Are there clues already?
Oh, absolutely. There are some really compelling examples. Take the TRIM5 gene. This gene helped our ancestors fight off a retrovirus that's now extinct. It was an evolutionary fix for a specific ancient problem. What's amazing is that scientists can now take that old code and re-edit it in the lab to make human cells much more resistant to HIV, a modern virus.
Wow, repurposing old evolutionary tools for new threats.
Exactly. It shows these genetic remnants aren't useless junk. They can be understood and potentially repurposed by us to tackle challenges evolution didn't prioritize, like current diseases or maybe even aspects of aging itself.
Okay, that's one example. What else points to this under-optimized idea?
Well, perhaps the most stunning example, the one that really drives home how much potential there might be, is for gene reprogramming, the Yamanaka factors. It turns out that activating just 4 specific genes out of roughly 20,000 in our genome can reset a cell's identity and, incredibly, its age. It can make an old cell young again, biologically speaking.
Only 4 genes out of 20,000.
Just 4. That's the mind-blowing part. It suggests that the controls for cellular age might be less complex, less distributed, less optimized than we ever imagined. It's not like you need to tweak thousands of things perfectly. Finding these few key master switches suggests that targeted interventions could have really profound effects. It points to that low-hanging fruit idea again.
So let's try and wrap this incredible journey up. The fundamental idea we've explored is that aging isn't some inevitable, perfectly crafted destiny. It's more like an evolutionary oversight.
Or perhaps a consequence of priorities. Evolution left it on the table, as you said earlier, not because solving it was impossible, but because, for most of history, the intense pressures of simply surviving early life, coupled with the biological trade-offs, made extreme longevity irrelevant or even costly for gene propagation.
But that very lack of optimization is what's so exciting now.
Exactly. That neglect by evolution opens this amazing window for biotechnology. We might be able to step in where evolution didn't, to target those under-optimized pathways, maybe even restore youthful function at a deep cellular level. It really reframes aging from an inevitability to potentially a treatable condition.
Which leaves us, and you, with a really profound thought to chew on. If aging isn't this fundamental biological necessity, but more like an evolutionary shortcut, a kind of design flaw left over from our species' rough past, what does that mean? What are the implications for how we see life, health, human potential? If our biological clock isn't set in stone, but might be adjustable, or even someday solvable, something fascinating to consider as science continues to unlock these secrets.